right. Today, let's go over what we're going to be reading today. So, writing secure privilege programs. So this is like dropping privileges using capabilities, probably. No, capabilities next section. So it's basically like dropping your privileges when you don't need them. Going over some of the best practices around set user ID and set group ID, probably. Principal of least privilege. It's always good for security. I wonder if they call out doing things like blocking or setting the disposition on the signals to ignore for the signals that do a core dump, and then disabling core dumps in general. That would be interesting. Beware of buffer overruns. Yeah. Capabilities. So capabilities are like sharding the privileges of root into these different capabilities that you can acquire instead of taking on the entire root set of privileges. Login accounting, I guess that's nice to know. A little bit of background on that because I don't really care about that stuff, so I don't really know much about it. So login accounting would be nice to read up on a little bit. This is like my medicine because I don't want to take it, but it's good for me. Fundamentals of shared libraries, advanced features of shared libraries. This is going to be the fun stuff. This will hit in the afternoon, and this is going to be super fun. I'm looking forward to that. And then an overview of IPC. So this is going to be the morning into capabilities, and then afternoon, and then evening. Cool. I'm getting a little bit started a little bit early today. Yesterday I got started at 9:50. So you can see 10:21, 10:04, 9:50, and now 9:25. So I'm starting earlier each day. And we're starting on, what page is this? 783. We're going to try to do another 100 pages today. Got my beverages here. I'm not going to spill them today. All right. Let's do this. Okay. Switch over to here. And let's get started. Actually, I'm going to hit the light because I need a little bit more light in here. All right. Writing secure privilege programs. Privilege programs have access to features like resources, files, devices, and so on that are not available to ordinary users. A program can run with privileges by two general means. The program was started under a privileged user ID. Many daemons and network servers, which are typically run as root, fall into this category. The program has a set user ID or set group ID permission bit set. When a set user ID, set group ID program is executed, it changes effective user and group ID of the process to be the same as the owner of the file. We first describe set user ID and set group ID programs in section 9.3. In this chapter, we'll sometimes use the term set user ID root to distinguish a set user ID program that gives super user privileges to a process from one that gives process another effective identity. If a privileged program contains bugs or can be subverted by a malicious user, then the security of the system or an application can be compromised. From a security viewpoint, we should write programs so as to minimize both the chance of a compromise and the damage that can be done if a compromise does occur. These topics form a subject for this chapter, which provides a set of recommended practices for secure programming and describes various pitfalls that should be avoided when writing privileged programs. Is set user ID and set group ID program required? One of the best pieces of advice concerning set user ID and set group ID programs is to avoid writing them whenever possible. If there's an alternative way to performing a task that doesn't involve giving a program privilege, we should generally employ that alternative since it eliminates the possibility of security compromise. Sometimes we can isolate the functionality that needs privilege into a separate program. Isolate the functionality that needs privilege in a separate program that performs a single task and exec that program in a child process as required. This technique can be especially useful for libraries. For example, one example of such use is provided by the PT-Chown program described in section 6422. So how would you go about doing that? You as a parent process, you would have to have the privileges to do it anyways. But you don't have to have them as effective. You can have them as your saved set UID. And your effective UID can be unprivileged. So you can just kind of drop your privileges. And then you can reclaim them when you fork. And then drop them in the parent. And then have the child retain them. And then have the child do its exec. I think that's the technique that he's kind of hinting at here. Even in cases where a set user ID or set group ID is needed, it's always necessary for a set user ID program to give a process root credentials. It isn't always necessary for set user ID to give root credentials. If giving a process some other credentials suffices, then this option should be preferred since running with root privileges often opens the gates to possible security compromise. Consider a set user ID program that needs to allow users to update a file on which they do not have permission to write permission. A safer way to do this is to create a dedicated group account, a group ID for this program, change the group ownership of the file to that group, and make the file writable by that group, and write a set group ID program that sets the process effective group ID to the dedicated group ID. Since the dedicated group ID is not otherwise privileged, it greatly limits the damage that can be done if a program contains bugs or it can otherwise be subverted. Yeah, it's a good idea. Down with that. Operate with least privilege. Set user ID or set group ID program typically requires privileges that privilege only to perform certain operations, while the program, especially one assuming super user privileges, is performing other work. While the program is performing other work, it should disable these privileges. When privileges will never again be required, they should be dropped permanently. In other words, a program should always operate with the least privilege required to accomplish the task that is currently performing. The save set user ID facility was designed for this purpose. Yep. Hold privileges only while they are required. In set user ID programs, we can use the following sequence of set EUID calls to temporarily drop and then reacquire privileges. So in this code, we get our effective user ID, and that is the original. And then we set our user ID to the real user ID. And then we can reacquire privileges later because we have that saved. Not because it's saved here, but it's also saved in the kernel as the save set user ID. Yeah, the first call makes the effective user ID. The first call makes the effective user ID of the calling process the same as its real ID. The second call restores the effective user ID to the value held in its save set user ID. For set group ID programs, the save set group ID saves the program's initial effective group ID. And set EGID is used to drop and reacquire privilege. We describe set EUID and set EGID and other similar system calls mentioned in the following recommendations, chapter 9. Summarize them in table 9.1. Safest practice is to drop privileges immediately on program startup and then temporarily reacquire them as needed at later points in the program. If at a certain point privileges will never be required again, then the program should drop them irreversibly by ensuring that the save set user ID is also changed. This eliminates the possibility of a program being tricked into reacquiring privilege, perhaps via the stack crashing technique described in section 38.9. Cool, we're going to talk about stack crashing. I'm not really terribly familiar with that, so that'd be cool to talk about. Drop privileges permanently when they are never needed again. They will never again be required. If a set user ID and set group ID program finishes all tasks that require privileges, then it should drop its privileges permanently in order to eliminate any security risks that could occur because the program is compromised by a bug or other unexpected behavior. Dropping privileges permanently is accomplished by resetting all process user group IDs for the same value as the real user group ID. One thing I need to constantly remember is that groups are primarily a permission feature around files and file system stuff, file-like things. They're not really a permission thing as far as like what syscalls a process can perform. That's those syscall checks are primarily based on what your effective and real user IDs are. All right, where would I leave off here? It was funny, yesterday I was like super tired in the afternoon when I was reading, and then like in the evening my brain just started lighting up. It's like I wish I could just have like super high energy from like morning to like late afternoon and then wind down and go to sleep. But it's like my stupid brain is just like usually I wake up with a decent amount of energy, and then noon hits and it kind of dips, and then it comes back. But yeah, it's odd, like the past, I would say, week. In the evenings, my brain is just like super hyperactive, just thinking about all these things, and like it's not good for my sleep. Alright, that's all my caffeine for the day, so hopefully that'll last me. Alright, let's see here. From a set user ID root program whose effective ID is currently 0, we can reset all of the user IDs to the following code. Set user ID to get ID is equal to -1. There is it's either a library syscall where you can set all 4 of them. I would personally prefer to use that thing because like there's the real, the effective, the save set, and the file system. And I would just like to have a library function that allows me to set all 4 instead of like, and you can pass in -1 or null as an argument. I think it's -1. Versus remembering all these different set UID, set EUID, set blah blah blah, EGID. For my set user ID program though, whose effective user ID is currently 0, we can reset all of the user IDs using the following code. So we're going to set the user ID to the get user ID. So that's saying whatever the actual real user ID is, set that to everything. Effective, save set, and file system. However, the above code does not reset the the save set user ID if the effective user ID of the calling process is currently non-zero. When called from a program whose effective ID is non-zero, set UID changes only the effective user ID. In other words, in a set user ID root program, the following sequence doesn't permanently drop user ID. So that's the thing. I just want the function that does exactly what it says in the 10 instead of all these silly functions that have evolved over time. Okay, so let's reread this just to make sure we get at least part of it. The above code does not reset the set user ID if the effective user ID of the calling process is currently non-zero. So we have to have our effective user ID set to 0. Then we have God mode, basically, to do whatever we want. And then we can call this set UID to get the real ID, the real user ID. And that'll set effective, save set, and file system. When called from a program whose effective ID is non-zero, set user ID changes only the effective user ID. In other words, the set user ID root program, the following sequence doesn't permanently drop the user ID 0. So initial ID is real, is at 1000, effective 0, save 0. So this is set UID root program. Usual call to temporarily drop privileges. So we say, hey, I'm going to get my effective user ID, which is 0, save it as the original. And if effective user ID, I'm sorry, I'm going to set the effective user ID to the real user ID, and then UID is changed to real effective saved. Looks like the right way to permanently drop privileges wrong, because then you could just go back, set UID, get UID, didn't make any changes. Okay. Instead, we must regain privileges prior to dropping it permanently by inserting the following call between steps 1 and 2. So we set our effective user ID back to root, and then we can make the call to set everything. On the other hand, if we have a set user ID program owned by a user other than root, then because set user ID is sufficient to change the saved set user ID, we must use either set RE UID or set RES UID. That's the one I like. Set RES UID. If there was an RESF UID, I would use it to permanently drop the privilege identifier. For example, we could achieve the desired result using set RE UID as follows. This code relies on a feature of the Linux implementation of set REUID. If the first RUID argument is not -1, then the save set user ID is also set to the same value as the new effective user ID. Substitute 3 doesn't specify this feature, but many other implementations behave the same way as Linux. Substitute 4 does specify this feature. The set RE GID and set RES GID system call must likewise be used to permanently drop a privileged group ID in a set group ID program, since when the effective user ID of a program is non-zero, set GID changes only the effective group ID of the calling process. If we do a man and say man set RES UID, is that set RES UID? Oh, sorry, I got an extra E there. Okay. And then if I say, is that in 2? Yeah, so that's a syscall. And if I say man syscalls and go to set RE, RES, and then set UID 32. There's like so many different. What I really want to do is, like, at some point grab this list of syscalls and start to categorize them. based on my knowledge of the book, like having knowledge of syscalls from the book, like go through and basically look at every single syscall and categorize them based on my knowledge, because a lot of these like are just horribly redundant and like huge API interfaces for very small amount of functionality. Like we're talking about 4 integers that we're managing here, and we have like so many different syscalls. It's insane. Okay. Where do we leave off? I think we left off here. General points. General points on changing process credentials. In the preceding pages, we described techniques for temporarily and permanently dropping privileges. We now add a few general points regarding the use of these techniques. The semantics of some of the system calls that change process credentials vary. Hold on a second. Sorry, my YouTube is glitching out here. All right. So they vary across systems. Furthermore, the semantics of some of these system calls vary depending on whether or not the caller is privileged. Effective user ID of 0. For details, see Chapter 9, especially Chapter 9.7.4. Because of these variations, so-and-so recommends the applicant should use a system-specific non-standard system calls for changing process credentials, since in many cases these non-standard system calls provide simpler and more consistent semantics than their standard counterparts. On Linux, this would translate to a set res UID. Yep, that's exactly what I was recommending to myself, to change user and group credentials. Although these system calls are not present on all systems, their use is likely to be less prone to error. So it proposes a library of functions that make credential changes using what they consider to be best interfaces available on each platform. On Linux, even if the caller has an effective user ID of 0, system calls for changing credentials may not behave as expected if the program has explicitly manipulated its capabilities. For example, if the cap set UID capability has been disabled, then attempts to change process user ID will fail, or even worse, silently change only some of the requested user IDs. I didn't know that you could do that. Oh. On my keyboard, right is right next to end, and every time I hit end, it goes to the end of the book. 786 is where we left off. 786, here we go. Alright. Because of the possibilities listed in the 2 preceding points, it's highly recommended practice to not only check that a credential changing system has succeeded, but also to verify that the change occurred as expected. For example, if we are temporarily dropping or reacquiring a privileged user ID using set EUID, then we should follow that call with a get EUID, that call that verifies that the effective user ID is what we expect. Similarly, if we're dropping a privileged user ID permanently, then we should verify that the real user ID and effective user ID and save set user ID have all been successfully changed to the unprivileged user ID. Unfortunately, while there are standard system calls for retrieving the real and effective IDs, there is no standard system call for retrieving the saved set IDs. Linux and a few other systems provide get res UID and get res GID for this purpose. On some other systems, we may need to employ techniques such as parsing information in proc files. Some credential changes may be made only by process with an effective user ID of 0. Therefore, when changing multiple IDs, supplementary group IDs, and user IDs, we should drop the privileged effective user ID last when dropping privileged IDs, of course. Conversely, we should raise the privileged effective user ID first when raising privileged IDs. Be careful when executing a program. Caution is required when a privileged program executes another program, either directly via an exec or indirectly via system, popen, or a similar library function. Drop privileges permanently before executing another program. If a set user ID or set group ID program execs another program, then it should ensure that all process user group IDs are reset to the same value as the real user group ID, so that the new program doesn't start with privileges and also can't reacquire them. One way to do this is to reset all the IDs before performing the exec using techniques described in section 38.2. Same result can be achieved by preceding the exec with the call set UID get UID, even though this set UID call changes only the effective user ID and the process whose effective user ID is non-zero. Privileges are nevertheless dropped because, as described in section 9.4, a successful exec goes on to copy the effective user ID into save set user ID. If the exec fails and the save set user ID is left unchanged, this may be useful if the program then needs to perform other privileged work besides the work because the exec failed. Similar approach, set GIDs, get GID can be used to set group ID programs, since this a successful exec also copies the effective group ID to the saved set group ID. As an example, suppose that we have a set user ID program owned by user ID 200. When this program is executed by a user whose ID is 1000, as an example, suppose that we have a set user ID program who is owned by user 200. When this program is executed by a user whose ID is 1000, these IDs of the resulting process will be 1000, 200, 200. Oops, sorry, I'm offset here. If this program subsequently executes the call set UID get UID, then the process user IDs are changed to the following: real 1000, effective 1000, saved 200. When the process executes an unprivileged program, the effective user ID of the process is copied to the save set user ID, resulting in the following set of user IDs: 1000 across the board. Avoid executing a shell or other interpreters with privileges. Privileged programs run under user control should never exec a shell. I do that all the time with sudo-i. Either directly or indirectly via system, popen, exec lp, exec vp, or other similar library functions. The complexity and power of shells and other unconstrained interpreters such as awk mean that it's virtually impossible to eliminate all security loopholes, even if the exec shell doesn't allow interactive access. The consequent risk is that the user may be able to execute arbitrary shell commands under the effective user ID of the process. If a shell must be executed, ensure that privileges are permanently dropped beforehand. An example of a kind of security loophole that can occur when executing a shell is noted in the discussion of system in section 27.6. A few Unix implementations honor the set user ID and set group ID permission bits when they're applied to interpreter scripts, so that when the script is run, the processor executing the script assumes the identity of one of the privileged users or some other privileged user. Because of the security risks just described, Linux, like some other Unix implementations, silently ignores the set user ID and set group ID permission bits when executing a script. Even on implementations where set user ID and set group ID scripts are permitted, their use should be avoided. Close all unnecessary file descriptors before an exec. In section 27.4, we noted that by default, file descriptors close all unnecessary file descriptors before an exec, or use the close exec open flag in file descriptor flag. In section 27.4, we noted that by default, file descriptors remain open across an exec. A privileged program may open a file that normal processes can't access. The result open file descriptor represents a privileged resource. The file descriptor should be closed before an exec, so that the exec program can't access the associated file. We can do this with either an explicit closing the file descriptor or by setting its close on exec flag. Sometimes you want to do this though. Like you want to get privileges to like listen, like bind to a privileged port, and then you can hand that like file descriptor over to an unprivileged process that you exec. Avoid exposing sensitive information. Let's see, how much do we got here? We got lots of cool little sections, small little sections. Okay, I'm going to take a quick break here, and then we'll resume at avoiding exposing sensitive information when I get back. I'll play some Zelda while I'm gone. All right. Avoid exposing sensitive information. When a program reads passwords or other sensitive information, it should perform whatever processing is required and then immediately erase the information from memory. We show an example of this in section 8.5. Leaving such information in memory is a security risk for the following reasons. The virtual memory page containing the data may be swapped out unless it is locked in memory using mlock or similar. It could then be read from the swapped area by a privileged program. A privileged program can also just read your memory using like proc pid mem or whatever. So it doesn't have to be swapped out. The problem with swapping is that it writes data to disk, and if the disk volume is not encrypted, then if there was like a power outage, they could just pull the disk and now they have your unencrypted password. If the process receives a signal that causes it to produce a core dump file, yeah, that's another problem, then that file may be read to obtain the information. Following on from the last point, as a general principle, a secure program should prevent core dumps. Yes, I'm so happy they covered this. So that a core dump file can't be inspected for sensitive information. A program can ensure that a core dump file is not created by using set R limit. Yes. So you just set that R limit to 0, and then there's no core dump. By default, Linux doesn't permit a set user ID program to perform a core dump in response to a signal. That's good. even if the program has dropped all privileges. However, other Unix implementations may not provide this security feature. Confine the process. In this section, we consider ways in which we can confine a program to limit the damage that is done if the program is compromised. Consider using capabilities. The Linux capability scheme divides the traditional all-or-nothing Unix privilege scheme into distinct units called capabilities. A process can immediately enable or disable individual capabilities, independently enable or disable individual capabilities by enabling just those capabilities that it requires. A program operates with less privilege than it would have if run with full root privileges. This reduces the potential for damage if the program is compromised. Furthermore, using capabilities and the secure bits flags, we can create a process that has a limited set of capabilities but is not owned by root. What is the secure bits flags? I gotta look that up in the index here. Hold on, give me 1 second. We haven't covered that yet. Let's see, signal EIH secure SEC. The sec bit knows. Okay. Secure bits flags 615. We covered that already? I don't remember that. 615. Let's go to 615. I'll just do it in the book here and read it out loud. 615. Oh, it was part of this huge freaking table that I skipped over. Yeah. It says effective exec and fork on process attributes. And 615 has miscellaneous Linux specific capabilities. I don't see secure bits anywhere here. But does it? Oh, here it is. Capability secure bits flags. So it's part of capabilities. Secure bits flags are preserved during exec. Okay, so it's part of capabilities. So I imagine we're going to be covering the next chapter. If we look back at the index, we got secure bits somewhere here. 801, 812 to 813, which is in the future. 801, 812 to 813. Yeah, this is in the capability section. Yeah, it's all in the capability section. But as a precursor to that, since I don't want to jump ahead, briefly explain secure bits in Linux. Secure bits are a set of per-process flags in Linux that fine-tune how privilege changes work, especially around UID transitions and capabilities. In short, they control whether gaining, losing root UID implicitly grants or drops privileges. Okay. Normally, switching to UID 0 automatically grants full privileges. Switching away drops them. Secure bits lets you disable or lock down that behavior. Common secure bits are no root. UID 0 is no longer automatically grants privileges. So you can be UID 0 with no privileges. Okay, that's good. Secure bit, no set UID fix up. These constants. Changing UIDs doesn't implicitly add or remove capabilities. Okay. Keep caps. Keep capabilities cross UID change, often used before dropping root. Secure bit star locked. Permanently lock the above bits so that they can't be changed later. Why they exist: support least privilege design, prevent accidental privilege regain, enable safer privilege dropping in daemons and containers, decouple being root from having power. Think of secure bits as guardrails on Linux privilege model, letting you say, even if this process becomes root later, don't trust it. Okay. Where do I leave off? Secure bit flags. Furthermore, using capabilities and the secure bit flags, we can create processes that have a limited set of capabilities but is not owned by root, i.e. all of its user IDs are non-zero. Such a process can no longer use exec to regain a full set of capabilities. We describe capabilities and the secure bit flags in chapter 29. Consider using chroot jail. The use of security technique in certain cases is establish a chroot jail to limit the set of directories and files that program may access. Make sure to also call change dir to change the process current working directory to a location within the jail. Note, however, that a chroot jail is insufficient to confine a set user ID root program. An alternative to using a chroot jail is a virtual server, which is a server implemented on top of a virtual kernel. Because each virtual kernel is isolated from other virtual kernels that may be running on the same hardware, a virtual server is more secure and flexible than a true root jail. Several other modern operating systems also provide their own implementations of virtual servers. The oldest virtualization implementation on Linux is user mode Linux, UML, which is a standard part of the Linux 2.6 kernel. Further information about UML can be found in user mode Linux sourceword.net. More recent virtual kernel projects include Zen and KVM. I've never heard of user mode Linux, but I've heard of Zen and KVM, obviously. Beware of signals and race conditions. A user may send arbitrary signals to a set user ID program that they have started. A user may send arbitrary signals to a set user ID program that they have started. Such signals may arrive at any time and with any frequency. We need to consider the race conditions that can occur if a signal is delivered at any point in the execution of the program. Where appropriate, signals should be caught, blocked, or ignored to prevent possible security problems. Furthermore, the design of signal handlers should be as simple as possible in order to reduce the risk of inadvertently creating a race condition. Design of signal handlers should be as simple as possible. Obviously. In fact, I would argue you don't even ever have to do signal handlers because there's all the syscalls that enable you to do a thread that can process signals instead of using a signal handlers. This issue is particularly relevant with the signals that stop a process. The problematic scenario is the following. A set user ID program determines some information about its runtime environment. Hold on, let me reread this. My mind was wandering there. This user is particularly relevant with signals that stop a process. The problematic scenario is the following. 1. A set user ID program determines some information about its runtime environment. The user manages to stop the process running the program and change details of the runtime environment. Such changes may include modifying the permissions on a file, changing the target of a symbolic link, or removing a file that the program depends on. The user resumes the process with continue signal. At this point, the program will continue execution based on now false assumptions about its runtime environment. These assumptions may lead to a security breach. The situation described here is really just a special case of a time of check, time of use race condition. A privileged process. So if you're using file descriptors, though, I mean, it kind of eliminates the whole time of check, time of use thing on files, at least. Because when you open a file, that's the time of check. You get back the file descriptor, and the file is now tied to the directly tied to the file descriptor is directly tied to the inode of the file. So it's not going to swap it out for some other file using symlinks or deleting and recreating the file or renaming it or anything. Okay. A privileged process should avoid performing operations based on previous verifications that may no longer hold true. Refer to the discussion. This is really really cool concept. I'm going to highlight that. Time of check, time of use, race condition. This guideline applies even when the user can't send signals to the process. The ability to stop a process simply allows the user to widen the interval between the time of the check and the time of use. Although it may be difficult on a single attempt to stop a process between the time of check and time of use, a malicious user could execute a set user ID program repeatedly and use another program or a shell script to repeatedly send stop signals to the set user ID program to change the runtime environment. This greatly improves the chances of subverting the set user ID program. Pitfalls when performing file operations in file I/O. If a privileged process needs to create a file, then we must take care of that file's ownership and permissions to ensure that there is never a point, no matter how brief, when a file is vulnerable to malicious manipulation. The following guidelines apply. The process UMask should be set to a value that ensures that the process never creates publicly writable files, since these could be modified by a malicious user. Since the ownership of a file is taken from the effective user ID of the creating process, judicious use of set EUID or set REUID to temporarily change the process credentials may be required in order to ensure that a newly created file doesn't belong to the wrong user. I think this is where you might want to manipulate the file system instead of the effective. Since the group ownership of the file may be taken from the process effective group ID, a similar statement applies with respect to set group ID programs, and the corresponding group ID calls can be used to avoid such problems. To be strictly accurate on Linux, the owner of a new file is determined by the process's file system user ID, which normally has the same value as process effective ID referred to section 9.5. If a set user ID root program must create a file that initially it must own, if a set user ID root program must create a file that initially it must own, but which eventually will be owned by another user, the file should be created so that it is initially not writable by other users, either by a suitable mode argument to open or by setting the process UMask before calling open. Afterwards, the program can change its ownership with the fchown and then change its permissions if necessary with fchmod. The key point is that a set user ID program should ensure that it never creates a file that is owned by the program owner, and that set user ID program should ensure that it never creates a file that is owned by the program owner and that is even momentarily writable by other users. Checks on file attributes should be performed on open file descriptors rather than by checking the attributes associated with the path name, and that opening the file stat followed by opening. The latter method creates a time of check problem. If a program must ensure that it is the creator of a file, then the O exclusive flag should be used when calling open. A privileged program should avoid creating or relying on files in publicly writable directories such as temp. Since this leaves the program vulnerable to malicious attempts to create unauthorized files with names expected by the privileged program. A program that absolutely must create a file in a publicly writable directory should at least ensure that the file has an unpredictable name by using a function such as mkstemp. Don't trust inputs or the environment. Oop. Did I skip ahead here? Sorry. I think I hit the wrong button there. My bad. Privileged programs should avoid making assumptions about the inputs they are given or the environment which they are running. Don't trust the environment list. Set user ID and set group ID programs should not assume that the values and environment variables are reliable. Two variables that are particularly relevant are path and IFS. Path determines where the shell and the system and popen, as well as exec LP and exec VP search for programs. A malicious user can set path to a value that may trick a set user ID program employing one of these functions into executing an arbitrary program with privilege. If these functions are to be used, path should be set to a trustworthy list of directories. But better still, absolute path names should be specified when executing programs. However, as already noted, it's best to drop privileges before executing a shell or employing one of the aforementioned functions. IFS specifies the delimiting characters that a shell interprets as separating the words of a command line. Interesting. So if I say echo $ifs, and if I pipe that into ODXA, I get back the new line character. That's because, sorry, that. So that means IFS is unset. How do I test if a bash variable is set? Test v IFS. Test v. So it's set, but it looks like its value is nothing. It's empty string, I guess. It's set to empty string. Okay. And it's not set to empty string in the concept of a C string. It's set to empty string in the concept of a bash string, which means that there's no null byte at the end of it. I don't like C strings. Like the null terminated strings, I do not like them. I like Go has the length prefix, the string header. I think they call those Pascal strings, where it's length prefixed. And I actually think Go's strings are represented as a string header that points to an area of memory with a length and potentially a capacity. Show me the struct for goes string header. Yeah. There's a pointer somewhere in memory and then length. And strings are immutable. Whereas byte slices, or slices in general, are pointed to somewhere in memory, the length of the elements of the slice, and its capacity of the underlying array. Alright, let's continue onward. So we're not trusting the environment. IFS specifies the limited characters that the shell interprets as separating the words of a command line. This variable should be set to an empty string, which it is. Which means that only whitespace characters are interpreted by the shell as word separators. Some shells always set IFS in this way on startup. In some cases, it may be the safest to erase the entire environment and then restore selected environment variables with known safe values, especially when executing other programs or calling libraries that may be affected by environment variable settings. Handle untrusted user inputs defensively. A privileged program should carefully validate all inputs from untrusted sources before taking action based on those inputs. Such validation may include verifying that numbers fall within acceptable limits and that strings are of an acceptable length and consist of acceptable characters. Among inputs that may need to be validated in this way are those coming from user-created files, command line arguments, interactive inputs, CGI inputs, email messages, environment variables, inter-process communication channels, FIFO, shared memory, and so on, accessible by untrusted users and network packets. Avoid unreliable assumptions about the process's runtime environment. A set user ID program should avoid making unreliable assumptions about its initial runtime environment. For example, standard input-output error may have been closed. These descriptors might have been closed in the program that execs the set user ID program. In this case, opening a file could inadvertently reuse descriptor 1, for example, so that while the program thinks it is writing to standard output, it's actually writing to the file it opened. There are many other possibilities to consider. For example, a process may exhaust various resource limits, such as the limit on the number of processes that may be created. The CPU time resource limit or file size resource limit, with the result that various system calls may fail or various signals may be generated. Malicious users may attempt to deliberately engineer resource exhaustion and attempt to subvert a program. Yeah, those are definitely like the edge cases where you can kind of trick programs into doing things, because programmers don't really consider edge cases as much as the happy path. Beware of buffer overruns. Beware of buffer overruns or overflows, where an input value or copied string exceeds allocated buffer space. Never use gets, and employ functions such as scanf, sprintf, strcpy, and strcat with caution, e.g. guarding their use with if statements that prevent buffer overruns. Buffer overruns allow techniques such as stack crashing, also known as stack smashing, whereby a malicious user employs a buffer overrun to place carefully coded bytes into a stack frame in order to force the privileged program to execute arbitrary code. Several online sources explain the details of stack crashing. See also so-and-so. Buffer overruns are probably the single most common source of security breaches on computer systems, as evidenced by the frequency of adversaries posted by CERT, and to bug track. Buffer overruns are particularly dangerous in network servers since they leave a system open to remote attack from anywhere on the network. In order to make stack crashing more difficult, in particular to make such attacks much more time consuming when conducting remotely against network servers from kernel 2612 onward, Linux implements address space layout randomization, ASLR. This technique randomly varies the location of the stack over a 8 megabyte range at the top of virtual memory. In addition, the locations of memory mappings may also be randomized. If the soft R-limit stack limit is not infinite, and the Linux-specific procsys VM legacy VA layout file contains the value 0, which it should on my machine. If I cat out proc sys VM legacy, yep. R limit stack. Stack size is unlimited. As a hard limit. So it says, in addition, locations of memory mappings may also be randomized if the soft, not the hard, the soft R limit stack limit is not infinite. More recent x86-32 architectures provide hardware support for marking page tables as NX no execute. This feature is used to prevent execution of program code on the stack, thus making stack crashing more difficult. Stack crashing more difficult. Yeah, that makes sense. You shouldn't be executing off the stack. But still, stack crashing or stack smashing seems like you could still get to jump to somewhere that is executable by like manipulating the stack return address, stuff like that. There are safe alternatives to many of the functions mentioned above. For example, snprintf, stirncopy, stirncat, that allow the caller to specify a maximum number of characters that should be copied. These functions take the specified maximum into account in order to avoid overrunning the target buffer. In general, these alternatives are preferable, but must still be handled with care. In particular, note the following points. With most of these functions, if the specified maximum is reached, then a truncated version of the source string is placed into the target buffer. Since such a truncated string may be meaningless in terms of semantics of the program, the caller must check if the truncation occurred, e.g. using return value from snprintf, and take appropriate action if it has, like putting a null byte at the end. Using stirncopy can carry a performance impact if, in the call stirncopy s2n, the string pointed to by 2 is less than n bytes length, then padding null bytes are written into S1 to ensure n bytes are in total are written. If the maximum size value given to stirncopy is not long enough to permit the inclusion of the terminating null character, then the target is not null terminated. Some Unix implementations provide the stirlcopy function, which given a length argument n copies at most n-1 bytes to the destination buffer and always appends a null character at the end of the buffer. However, this function is not specified in Subspeed 3 and is not implemented in glibc. Therefore, in cases where the caller is not careful checking string lengths, this function only substitutes one problem buffer overflows for another, silently discarding data. Beware of denial of service attacks. With the increase of internet-based services has come a corresponding increase in the opportunities for remote denial of service attacks. These attacks attempt to make a service unavailable to legitimate clients, either by sending the server malformed data that causes it to crash, or by overloading it with bogus requests. Local denial of service attacks are also possible. The most well-known example is when a user runs a simple fork bomb, a program that repeatedly forks, thus consuming all the process slots in the system. However, the original local denial of service attack is much easier to determine. However, the origin of local denial of service attack is much easier to determine. The origin, sorry. Okay, my mind was wandering there. That's why I got distracted. However, the local. Why can't I read this? However, the origin of local denial of service attacks is much easier to determine, and they can generally be prevented by suitable physical and password security measures. Dealing with malformed requests is straightforward. A server should be programmed to rigorously check its inputs and avoid buffer overruns as described above. Overload attacks are more difficult to deal with since the server can't control the behavior of remote clients, or at the rate at which they submit requests, such attacks are impossible to prevent. The server may not even be able to determine the true origin of the attack, since the source IP address of the network packet can be spoofed. Alternatively, distributed attacks may enlist unwitting intermediary hosts to direct attack against the target system. Nevertheless, various measures can be taken to minimize the risk and consequence of an overload attack. Run Kubernetes. Horizontally scale out. Do protocol sanitization. Use Cloudflare. The server should perform load throttling, drop requests when the load exceeds some predetermined limit. This will have the consequence of dropping legitimate requests, but prevents the server and host machine from becoming overloaded. The use of resource limits and disk quotas may also be helpful in limiting excessive loads. Refer to Linux quota for more information on disk quotas. Reading this reminds me of one of my first professional gigs. I deployed a server that was horribly under-resourced, and it got a massive amount of traffic and crashed. Yeah, it was not a good time. Okay. A server should employ timeouts for communication with the client, so that if the client, perhaps deliberately, doesn't respond, the server is not tied up indefinitely waiting on the client. That's something that I'll highlight because it happens more often than you would think, that timeouts are not set. In fact, it should be the default that timeouts are set, but it's not in many network libraries. In the event of an overload, the server should log suitable messages so that the system administrator is notified of the problem. However, logging should be throttled so that logging itself doesn't overload the system. The server should be programmed so that it doesn't crash in the face of an unexpected load. For example, bounds checking should be rigorously performed to ensure that excessive requests don't overflow a data structure. Data structures should be designed to avoid algorithmic complexity attacks. Interesting. For example, a binary tree may be balanced and deliver acceptable performance under typical loads. However, an attacker could construct a sequence of inputs that result in an unbalanced tree, the equivalent of linked list in the worst case, which could cripple performance. So-and-so details the nature of such attacks and discusses data structuring techniques that can be used to avoid them. Check return statuses. This idea of algorithmic complexity attacks is kind of a cool idea. I'll highlight that. Check return statuses and fail safely. A privileged program should always check to see whether a system call and a library function succeed and whether they return expected values. This is true for all programs, of course, but is especially important for privileged programs. Various system calls can fail, even for a program running as root. For example, fork may fail if the system-wide limit on the number of processes encountered. And open for writing may fail on a read-only file system, or chadir may fail on a target directory if a target directory exists. Doesn't exist, sorry. Even where a system call succeeds, it may be necessary to check, its result. For example, where it matters, a privileged program should check that a successful open has not returned one of the three standard file descriptors, 0, 1, or 2. Finally, if a privileged program encounters an unexpected situation, then the appropriate behavior is usually either to terminate, or in the case of a server, to drop the client request. Attempting to fix unexpected problems typically requires making assumptions that may not be justified in all circumstances and may lead to the creation of security loopholes. In such situations, it's safer to have the program terminate or to have the server log a message and discard the client's request. Summary. Privileged programs have access to system resources that are not available to ordinary users. All right. Sorry, my mind's wandering. Summary. Privileged programs have access to system resources that are not available to ordinary users. If such programs can be subverted, then the security of the system can be compromised. In this chapter, we present a set of guidelines for writing privileged programs. The aim of the guidelines is twofold: to minimize the chances of a privileged program being subverted, and to minimize the damage that can be done in the event that a privileged program is subverted. McGraw et al. Covers a broad range of topics related to design, implementation of secure software. General information about security on Unix systems, as well as chapter on secure program techniques, can be found in so-and-so. Computer security is covered in some length in so-and-so and even greater length. Bishop describes computer security with a focus on various means by which systems may be attacked. Provide a thorough discussion on various security exploits. Okay, great. None of those are really up to date. Several security sources of information about writing secure programs are available online, including the following. Cool. Exercises. Log in as a normal unprivileged user, create an executable file or copy an existing file such as bin sleep, and enable the set user ID permission bit on that file, chmod u plus s. Try modifying the file. What happens to the file permissions as a result of LSL-L? Why does it happen? Okay, we'll do that one. So I'm in my home directory. I'm gonna just jump over to TLPI, and we'll do as they say. CP bin sleep. Log in as a normal user. Create an executable, copy existing test. So lsleg test. So I own this file, and then I'm gonna do a chmod u plus s test. That should be just the set use ID permission should be set, so the x should be changed to whatever it is, s. Yeah. So now I say cat into test. Cat into test. Hello. Oh, it removed the set user. Run test. That's mkdir chapter 38. cd into there. Vim exercises.txt. And then, oops, we say 38-1. It removed the set user ID bit. Why does it happen? Well, I would assume the kernel does this because at the time of setting this bit, you were authorizing a specific binary to run with set user ID. Once that file has changed, even by the same user that created it, that owns it, by the owner of that file, it is now a new binary that isn't authorized. This must be a security measure on Linux by the kernel. Let's say by the kernel. Okay, and then I need to go in here. I need to do a little monkeying around here to fix this, and I have to do Shift V G. Oops, sorry. Shift V G W J. Shift V G. Oh, Shift V G W J. Shift V G W J. Oops. There we go. That's my answer, and I'm sticking to it. Let's see what the book says. 38.1. Whenever a file is modified by an unprivileged user, the kernel clears the file's set user ID permission bit. The set group ID permission bit is similarly cleared if the group execute permission bit is enabled. The combination of having the set group bit on while the group execute bit is off has nothing to do with the set group ID programs. Instead, it is used to enable mandatory locking, and for this reason, modifications to such a file don't disable the set group ID bit. Clearing these bits ensures that if the program file is writable by arbitrary users, then it can't be modified and still retain its ability to give privileges to users executing the file. A privileged cap F set ID process can modify a file without the kernel clearing these permission bits. Okay. Makes sense. I'm happy with my answer. It's not exactly perfect, but well, messed it up again. Okay, we're going to 797. There we go. There we go. Write a program. Nope, not doing that. Don't have time for it. 39 capabilities. So it is 10:42 now. And we are at what, 797, 10:42. So that would be what? $14 pages in a little over an hour and 15. Yeah. Not bad rates. I think 15 pages in an hour If we do 100 divided by 15, that is 6.6 hours. So that's our standard rate that we got to go by here. Capabilities, 39. This chapter describes the Linux capabilities scheme, which divides the traditional all-or-nothing Unix privilege scheme into individual capabilities that can be independently enabled or disabled. Using capabilities allows a program to perform some privilege operations while preventing it from performing others. Oh, got a spammer. Okay. So it looks like you have like granting capabilities and dropping them, which is preventing them from ever getting them type deal. But I don't have a lot of experience, only like dropping them for security reasons. Okay, the traditional Unix privilege scheme divides processes into two categories. Those with effective user ID is 0, superuser, which bypass all privilege checks, and all other processes which are subject to privilege checking according to their user and group IDs. The coarse granularity of the scheme is a problem. If we want to allow a process to perform some operation that is permitted to only to the superuser, for example, changing system time, then we must run that process with an effective user ID of 0. If an unprivileged user needs to perform such operations, this is typically implemented using a set user ID root program. However, this grants the process privileges to perform a host of other actions as well, for example, bypassing all permission checks when accessing files, thus opening a door for a range of security breaches if the program behaves in unexpected ways, which may be the consequence of unforeseen circumstances or because of deliberate manipulation by a malicious user. The traditional way of dealing with this problem was outlined in Chapter 38. We drop effective privileges, i.e. change from an effective user ID of 0 while maintaining 0 in the save set user ID. And temporarily reacquire them only when needed. The Linux capability scheme refines the handling of this problem. Rather than using a single privilege, i.e. effective user ID of 0, when performing security checks in the kernel, the superuser privilege is divided into distinct units called capabilities. Each privileged operation is associated with a particular capability. And a process can perform that operation only if it has the corresponding capability, regardless of its effective user ID. Put another way, everywhere in this book that we talk about a privileged process on Linux, what we really mean is a process that has the relevant capability for performing a particular operation. Most of the time, Linux capability scheme is invisible to us. The reason for this is that when an application that is unaware of capabilities assumes an effective user ID of 0, the kernel grants that process a complete range of capabilities. The Linux capabilities implementation is based on the POSIX 1003. Should that be 2003? So that was based on the date, the year. Anyways, this draft standard, maybe the drafts are 100. Okay. This standardized effort foundered in the late 1990s before it was completed, but various capabilities implementations are nevertheless based on this draft standard. Some of the capabilities listed in Table 39.1 are defined in POSIX 1E draft, but many are Linux extensions. Capability schemes are provided in a few other Unix implementations, such as the Sun Solaris 10 and earlier Trusted Solaris releases, SGI Trusted ERIX, and as part of the Trusted BSD project for FreeBSD. Similar schemes exist in some other operating systems, for example, the Privilege Mechanism Digital's VMS system. The Linux capabilities. Table 39.1 lists the Linux capabilities and provides an abbreviated and incomplete guide to the operations to which they apply. 39.1, where is that table? Oh god, that's a big table. 2 pages, okay. I actually might read the whole table, because I'm kind of curious about capabilities. Process and file capabilities. Each process has 3 associated capability sets, termed permitted, effective, and inheritable. Oh god, we're getting super complicated already. This already got like all those, effective, real effective save set and file system user IDs and group IDs and supplementary group IDs. Now it's permitted, effective, and inheritable. Okay. These are the different sets. Whether something is permitted, whether it's effective. Effective means that you probably are currently running with it. Permitted is kind of like the save set. And inheritable means that when you fork, your children get, you fork or clone, your children get the same effective, probably something like that. I'm just guessing here. So each process has 3 associated capability sets, termed permitted, effective, and inheritable, that contain 0 or more of the capabilities listed in table 39.1. Each file can likewise have 3 associated capability sets. So a process can have that, and a file can have that with the same names. For reasons that will become evident, the file effective capability set is really just a single bit that is either enabled or disabled. We go into details of each of these capability sets in the following sections. Process capabilities. For each process, the kernel maintains 3 capability sets implemented as bit masks, in which 0 or more of the capabilities specified in table 39.1 are enabled. The 3 sets are as follows. Permitted. These are the capabilities that a process may employ. The permitted set is a limited superset of the capabilities that can be added to the effective and inheritable sets. My mind's wandering, thinking about some other things right now. Okay, okie dokie. Permitted. These are the capabilities that process may employ. The permitted set is a limited superset is a limiting superset for the capabilities that can be added to the effective and inheritable sets. If a process drops a capability from its permitted set, it can never reacquire the capability unless it execs a program that once more confers the capability. Okay. Effective. These are the capabilities used by the kernel to perform privilege checking for the process. As long as it maintains a capability in its permitted set, a process can temporarily disable the capability by dropping it from the effective set and then later restoring it to that set. Inheritable. These are capabilities that may be carried over to the permitted set when a program is exec'd by this process. We can view hexadecimal representations of the 3 capability sets for any process in the 3 fields: cap inherited, cat permitted, and cap effective, and a Linux specific proc pid status file. I did see those earlier. Proc PID self status. And we'll just grep for cap. No cap. So we also have cap B and D and cap A and B, which we have not covered yet in the book. And I'll ask AI, explain B and D and A and B briefly. Bounding set, the upper limit of capabilities of process and any of its children can never gain. Ambient set. So bounding bounds the process and all of its trees to that set. And you're not getting anything more than that set, no matter what. What if a process is inherited by init because it is orphaned? Does the bounding set still apply? Okay. File cap. I wonder if they use extended attributes to do that. Okay. We'll come back to that. That would explain why bounding is like has so many bits set, because we don't want to bind it too much for just like a regular shell process. I'm sure there's some things that we shouldn't allow. Okay. Get cap program. Get cap on PID there. No, that's file name. Okay. The get caps program might get cap. Get caps. Get cap. The get caps program, part of the libcap package, can be used to display capabilities of a process in an easier to read format. That thing don't exist, bro. A child process produced via fork inherits copies of its parents' capability sets. We described the treatment of the capability sets during an exec section 39.5. In reality, capabilities are per thread attribute that can be adjusted independently for each of the threads in a process. The capabilities of a specific thread within a multi-threaded process are shown in the procpid task TID status file. The procpid status file shows the capabilities of the main thread. Before Kernel 2625 Linux represented capability sets using 32 bits. The addition of further capabilities in kernel 2625 require the move to 64-bit sets. File capabilities. If a file has associated capability sets, then these sets are used to determine the capabilities that are given to a process if it executes that file. There are 3 file capability sets: permitted, effective, and heritable. Same thing. Permitted is a set of capabilities that may be added to the process's permitted set during exec, regardless of the process's existing capabilities. Effective, this is just a single bit. If it's enabled, then during exec, the capabilities that are provided in process permitted set are also enabled in the process's new effective set. If the file's effective bit is disabled, then after the exec, the process's new effective set is initially empty. Inheritable, this set is masked against the process's inheritable set to determine a set of capabilities that are to be enabled on the process permitted set after an exec. Section 39.5 provides details of how file capabilities are used during an exec. The permitted and inheritable capabilities are formally known as forced and allowed. Those terms are now obsolete, but they are still informative. The permitted file capabilities are the ones that are the permitted file capabilities are the ones that are forced into the process's permitted set during exec, regardless of the process's existing capabilities. The inheritable file capabilities are the ones that the file allows into the process's permitted set during an exec, if those capabilities are also enabled in the process's inheritable capability set. The capabilities associated with a file are stored in a security extended attribute named security capability, and cap set fcap capability is required to update this extended attribute. Yeah, it's extended attribute. And then this is a table of all the different capabilities. I'm gonna just say like no. I'm not gonna read all this. Cap kill, that's important. Cap sysadmin I've ran into before. Cap sysadmin I've always considered as being basically root. But I guess it's not. I mean, why would it be basically root if you if you wanted to shard up the root privileges, you wouldn't have a capability that gives you everything. Capsys ptrace I've run into before. I think that's about it. That's in this list here. Okay. Purpose of the process permitted and effective capability sets. Oh, okay. I feel like I'm slowing down here on the capability stuff. Okay. Well, we're in the 800s. That's something to celebrate. The process permitted capability set defines the capabilities that a process may employ. The process effective capability set defines the capabilities that are currently in effect for the process. That is, a set of capabilities that the kernel uses when checking whether the process has necessary privilege to perform a particular operation. The permitted capability set imposes an upper bound on the effective set. A process can raise a capability in its effective set only if that capability is in the permitted set. The terms add, to, and set are sometimes used synonymously with raise. The converse operation is drop, or synonymously remove or clear. The relationship between the effective and permitted capability set is analogous to that between the effective user ID and the save set user ID for the set user ID program. Yeah, it makes sense. Dropping a capability from effective set is analogous to temporarily dropping effective user ID of 0 while maintaining 0 in the save set user ID. Dropping a capability from both the effective and permitted capability sets is analogous to permanently dropping super user privileges by setting both the effective and user ID and save set user ID to non-zero values. Purpose of the file permitted and effective capability sets. So, with the regular process credentials, the thing about Unix and Linux is that only processes have credentials. Like, there isn't really a concept of a user having a credential. Everything that's running on the computer is a process. Like, you are not running on the computer. So, while there is a concept of a user, it's only a mechanism for providing credentials to a process. The process is the thing. The process and its relationship to other processes is the thing that is being authorized. And so with the set UID and set GID bits, what you're doing is saying allow the file system to affect those process credentials. Similarly, with capability sets, again, the process is the thing. It has capabilities, or it has doesn't have them. And the parent or a process that has privilege can modify those sets of capabilities, but ultimately, like, it's a process that is the thing. There is no other concept. The process has the capability or not. And the file system capabilities, it's just metadata that's stored in extended attributes that say when you run this program, when you exec it, these settings should affect the runtime values of the capabilities. So it's a similar mechanism, just has more granularity and more information, so it's less constrained. All right, so let's go back and with that in mind, resume reading from 3934. I feel like this is like the Torah. Like I'm reading scripture here. Even the pages, they're like, I remember when I used to go to church, my pastor used to always say, like, oh, it's the sound of angels' wings. It's like, even these pages are like the same thickness of like a page from a Bible. Purpose of the file permitted and effective capability sets. The file permitted capability set provides a mechanism by which an executable file can give capabilities to a process. It specifies a group of capabilities that are assigned to the process permitted capabilities set during an exec. The file effective capability set is a single bit flag that is either enabled or disabled. To understand why this set consists of just a single bit, we need to consider the two cases that occur when a program is exec. The program may be capability dumb, meaning that it doesn't know about capabilities, i.e. is designed as a traditional set user ID root program. Such a program won't know that it needs to raise capabilities in its effective set in order to be able to perform privileged operations. For such programs, I want to do a little experimenting here. I want to find a program, write me a script that finds programs on my computer, Linux workstation, that have file permitted capability sets. So we establish the root there that we're going to scan from, and then we call get capability get cap, man get cap, -r recursive search on the root there. Okay, get cap recursive on bin. Do I have to sudo that? Bin, I'll just say root to dev null. Get cap on user bin btop, and if I ls-la under user bin and we look at btop, it should have an @ sign on it. Oh, there's lots of things here. Let's put this into a pager, and then we'll look through from the top down because it's B. But it should have an @ symbol. Btop. Come on, btop. There we go. Boop. And then if we do get fadder on user bin btop. Wait a minute. Isn't that the right thing? Man get fadder? Sudo? Okay, I found a file with @ set in its output in ls, from ls, and get cap returns some caps, but nothing is returned from get fadder. I thought caps were stored as extended attributes. They live in a special xadder namespace that hides. Oh, okay. Man get fadder. So this is user stuff. I want everything. Is there -a? Dump. Let's do -d. Is capd? No. I could just look at AI and see what it says, but Sudo? O-M, man, let's do man get f adder m pattern match. Okay, so you gotta do this or else it'll oops, sorry, m dash. Okay, there we go. And then I can do dm to dump it. And of course it's base64 encoded binary. Cool. Give me 1 second here. I'm going to try something on my main computer. I'm just running a program on my workstation that is searching for ACLs stored on any file on my computer, because I'm curious if they're actually in use anywhere. Like the capabilities are being used like on specific programs like we saw, but I've never really ran into ACLs in the wild. Seems like most things just fall under the traditional permission model, and ACLs are kind of overkill. Yeah, this program, I'll just let it run on my computer and see if it returns anything. Sorry, I'm a little bit distracted here. Oh, here we go. Program has results. Okay, there are a lot of files. I'll have to come back to that. All right. Let's go back to reading. Okay, we were talking about capability dumb programs. And then we searched our computer and we see like, okay, there are quite a few programs that have these capabilities set, including BTOP. And if we ls on BTOP, ls-la pipe in the, or no, we can just do like this, right? So it has the capability set. It does not have set user ID or set GID set. And it does have user roots, and its group is root as well. Okay, let's resume at the capability dumb section. The program may be capability dumb, meaning it doesn't know about capabilities, i.e. it is designed as a traditional set user ID root program. Such a program won't know that it needs to raise capabilities in its effective set in order to be able to perform privileged operations. For such programs, an exec should have the effect that all the process's new permitted capabilities are automatically also assigned to its effective set. This result is achieved by enabling the file effective bit. The program may be capability aware, meaning that it is designed with the capabilities framework in mind, and it will make the appropriate system calls discussed later to raise and drop capabilities in the effective set. For such programs, least privilege considerations mean that after an exec, all capabilities should initially be disabled in the process's effective capability set. This result is achieved by disabling the file effective capability set. Purpose of the process and file inheritable sets. So that's the file permitted and effective, the inheritable sets. At first glance, the use of permitted and effective sets for processes and files might seem as sufficient framework for a capability system. However, there are some situations where they do not suffice. For example, what if a process performing an exec wants to preserve some of its current capabilities across the exec? It might appear, that the capabilities implementation could provide this feature simply by preserving the process permitted capabilities across an exec. However, this approach would not handle the following cases. Performing the exec might require certain privileges, e.g. cap DAC override, that we don't want to preserve across the exec. Suppose that we explicitly drop some permitted capabilities that we don't want to preserve across the exec, but then the exec failed. In this case, a program might need some of the permitted capabilities that it already irrevocably dropped. For these reasons, the process permitted capabilities are not preserved across an exec. Instead, another capability set is introduced, the inheritable set. The inheritable set provides a mechanism by which a process can preserve some of its capabilities across an exec. The process inheritable capability set specifies a group of capabilities that may be assigned to the process's permitted capability set during an exec. Corresponding file inheritable set is masked ANDed against the process's inheritable capability set to determine the capability set that are actually added to the process permitted capability set during an exec. There is a further philosophical reason for not simply preserving the process's permitted capability set across an exec. The idea of the capability system is that all privileges given to a process are granted or controlled by the file that the process execs. Although the process inheritable set specifies capabilities that are passed across an exec, these capabilities are masked by the file's inheritable set. Okay. Assigning and viewing file capabilities in the shell. We already kind of explored this on our own, but the setcap and getcap commands contained in the libcap package described in section 39.7 can be used to manipulate file capability sets. We demonstrate the use of these commands with a short example using the standard date program. This program is an example of a capability dump application according to the definition in section 39.3.4. When run with privileged date, can be used to change the system time. The date program is not set user ID root, so normally the only way to run it with privilege is to become the super user. We begin by displaying the current system time and then try to change the time as an unprivileged user. Above, we see that date command failed to change the system time, but nevertheless displayed its argument in the standard format. Next, we become the super user, which allows us to successfully change the system time. Hooray! We now make a copy of the date program and assign it the capability that it needs. What is this? Where is btop? Does that work? Man, where is? Binary source and manual page file for command. Binary source. What is LSHLA user share btop? What is that? Okay. Okay. where are we? Okay, we're reading this script here. So whereas -b date, what does the -b flag do for whereas? Search for binaries. So if I do whereas b top, just gives you back the binary, not the man pages. Okay. The cp bin date into current directory, and then we sudo set cap systime pe, which is the permitted and effective date. We then type in our root, and then we say, hey, get cap, which means cap sysadmin granted for effective and permitted. The set cap command shown above assigns the cap systime capability to the permitted P and effective capability sets of the executable file. When we then use the get cap command to verify the capabilities assigned to the file. The syntax used by set cap and get cap for representing capability sets is described in the cap from text manual page provided in the libcap package. The file capabilities of our copy of the date program allow the program to be used by unprivileged users to set the system time. That's pretty cool. The modern capabilities implementation. A complete implementation of capabilities requires the following. For each privileged operation, the kernel should check whether the process has the relevant capability rather than checking for an effective or file system user ID of 0. The kernel must provide system calls allowing a process capabilities to be retrieved and modified. The kernel must provide system calls allowing a process capabilities to be retrieved and modified. The kernel must support the notion of attaching capabilities to an executable file so that the process gains the associated capabilities when that file is exec. This is analogous to the set user ID bit, but allows an independent specification of all capabilities on the executable file. In addition, the system must provide a set of programming interfaces and commands for setting and viewing the capabilities attached to an executable file. Up to and including kernel 2.6.23, Linux met only the first two of these requirements. Since kernel 2.6.24, it is possible to attach capabilities to file. Various other features were added in kernels 2.6.25 and 2.6.26 in order to complete the capabilities implementation. For most of our discussion of capabilities, we'll focus on the modern implementation. In section 39.10, we consider how the implementation differed before file capabilities were introduced. Furthermore, file capabilities are an optional kernel component in modern kernels, but for the main part of our discussion, we'll assume that the component is enabled. Later, we'll describe the differences that occur if file capabilities are not enabled. In several respects, the behavior is similar to that of Linux and kernels before 2.6.24, where file capabilities were not implemented. In the following sections, we go into more detail on the Linux capabilities implementation. Transformation of process capabilities during exec. This is where we get into some actual code of how this stuff gets applied. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pages left. 10 pages left on capos. Okay, I'm gonna take a break, I think here. Yeah, because I'm getting a little hungry. I had a light breakfast, so I'm gonna take my break here, and I'll be an hour and a half. So I'll be back on at 1 p.m. Because I'm gonna be doing my cardio as well. So I'll get back on at 1 p.m. and then we'll go for several more hours there. So this is 8:05. And we are at 11:34. How many pages do we have left? So if we're going for 880, oops, messed that up, my bad. If we're going for 882 minus 805, it's going to be 77 pages left out of 100, divided by 15 pages an hour, roughly. So So we got about more than 5 hours left. 6 hours. So if you add 6 onto 1, that'd be 7 p.m. I'd be getting done. I might not be able to hit 100 pages today. We'll see. We'll see. We'll see. But yeah, let me go ahead and grab lunch then. Come back. I will resume capabilities. Let's see. Where are we at here? 8:05. There we go. All right. We'll pick up back from transformation process capabilities learning exec. So this is going to be a bunch of stuff like, let's see, effective process capabilities like changing user IDs, changing process capabilities programmatically. This is now the API, some code examples, create capabilities only environments, discovering the capabilities required by a program, old kernels and systems without file capabilities, and summary. And then we got our login accounting that we need to get through. So we got through this chapter and some of this chapter here, half of this. And then we got to get through the remaining half, login accounting. And then we get to shared libraries and IPC in the last session of the day. Okay, I'm excited. I'm going to go grab some lunch and I'll be back at 1 p.m. in an hour and a half.